October 3rd, 2025. For the first time since Oumuamua startled astronomers in 2017, the solar system hosts another confirmed interstellar visitor, 3I/Atlas. On this day, it skims just 0.2 astronomical units from Mars, roughly 29 million kilometers, a distance close enough for detailed observation by multiple orbiters and rovers. Dozens of telescopes around Earth and Mars stand ready, yet curiously, the only publicly confirmed evidence comes from a single faint streak detected in Perseverance's night sky imaging sequences by two independent analysts. Beyond that, silence. Despite promised coordination from NASA, the European Space Agency, ESA, China's CNSA, and the United Arab Emirates HOPE mission, no official imagery or spectra are released. Did humanity truly glimpse the chemistry of an interstellar comet? Or did the closest look yet slip forever out of reach? The stakes for planetary science and for our preparedness for future interstellar visitors have never been higher. At its closest pass, 3I/Atlas blazed through the Martian sky at over 60 kilometers per second, nearly 3 times the speed of an average long-period comet. The geometry was unforgiving, a 5-day observational window before the object vanished into the glare of the sun. For planetary scientists, this was a once-in-a-century opportunity. Never before had an interstellar object come within range of a fully equipped planetary observation network. From the Mars Reconnaissance Orbiter's HiRISE camera to ESA's Mars Express, the UAE's HOPE probe, and China's Tianwen-1 orbiter. Each team scrambled to retarget instruments, recalculating ephemerides with microsecond precision. Observation sequences were rewritten overnight, one miscalculation, and the target, moving against the Martian backdrop faster than any natural comet ever recorded, would slip by unseen. If successful, the data could have been revolutionary. High-resolution imagery might reveal the coma's morphology, the dust jets, even fragmentation signatures from tidal stress. Spectrometers could isolate exotic ices, perhaps ammonia hydrates, complex hydrocarbons, or deuterium to hydrogen ratios inconsistent with any body formed in the solar system. A single well-timed spectrum could tell us if 3I/Atlas was forged in the disk of another star, or if, as some theories propose, it was ejected debris from a disrupted exoplanetary system millions of years ago. For researchers, it was not just an astronomical event, it was a scientific gamble with cosmic stakes, a rare alignment of technology, timing, and luck. But as the flyby unfolded and Mars's instruments fell silent, the flood of expected data never came, and the world was left waiting, watching, wondering what Mars had seen. A faint, diffuse signal in the Martian night sky, that was all Perseverance's Mastcam-Z camera captured of 3I/Atlas in the hours following its closest approach. No radiant trail, no dramatic flare, just a whisper of light barely distinguishable from background noise. The first to extract and publicly confirm the detection were Stephen Burns, a geologist and longtime image analyst, and Simon Stimson, a meticulous amateur known for his precision in planetary imaging. Working entirely independently, both downloaded the raw Mastcam-Z frames from NASA's Public Planetary Data System PDS within hours of downlink. Their process was simple in concept, but painstaking in execution. They combined dozens of long exposure frames, each roughly 29 seconds in duration, taken between October 3rd and 4th, 2025. In total, 76 usable images were logged across both nights. Each exposure was aligned against the Martian star field, using reference points from the Gaia DR3 catalog adjusted for the rover's local horizon. Noise suppression came next. Each science frame was paired with its nearest dark calibration image, subtracting sensor bias pixel by pixel. Then came flat field correction, compensating for the uneven sensitivity of Mastcam-Z's detectors, and for micron-sized dust grains coating the optics after years of operation on the surface. Once stacked, the aligned composite began to reveal a subtle patch of light at the predicted coordinates of 3I/Atlas. No visible structure, no outburst, just a tiny blurred point surrounded by a weak coma, exactly where orbital projections said it should be. Burns and Stimson released their results with careful restraint. Their annotated image, more a scientific data set than a photograph, was posted to X, formerly Twitter, and Blue Sky, complete with overlays of predicted comet positions, time-stamped coordinates, and links to their Python calibration scripts. The duo emphasized transparency, urging others to reproduce the result. In planetary science, this kind of auditable workflow is crucial. It turns a faint smudge into credible evidence. The outcome was neither a sensational discovery nor a disappointment. It was a measured triumph of open data and persistence, a reminder that even amid institutional silence, a dedicated few with patience, code, and access to public archives can still extract truth from the noise. The full audit trail was clear. October 3rd, 36 frames captured between 2100 and 2330 local Mars time. October 4th, 40 additional frames under similar sky conditions. Integration time, approximately 2,200 seconds total. Estimated apparent magnitude around plus 12.4, consistent with pre-flyby predictions. Subpixel registration ensured each star aligned within 0.05 arc seconds of its reference point. Enough precision to make a 1 pixel wide deviation meaningful. And there, in that calibrated stack, the faint central glow of 3I/Atlas endures, the only surface-based optical confirmation of the interstellar object's passage. Not a revelation, not a failure, but a quiet proof of concept. That discovery now belongs to anyone willing to look closely enough. Outlier rejection, sigma clipping, and median filtering were applied to eliminate cosmic ray strikes and transient hot pixels. Each frame was carefully masked to flag residual artifacts, a process that left only clean, calibrated data ready for stacking. With the aligned data set in hand, Burns and Stimson produced dual composite stacks, one using median integration to suppress random noise, and another using mean averaging to retain faint extended structure. This dual approach maximized the signal-to-noise ratio, SNR, while guarding against overfitting random fluctuations into false positives. A modeled sky background, built from control regions away from the predicted target coordinates, was subtracted to reveal only those sources marginally above the statistical detection threshold. The result, a barely perceptible, slightly diffuse spot at the predicted position of 3E/Atlas, matching pre-flyby ephemerides within 0.04 arcseconds, well inside astrometric error. Photometric extraction confirmed the detection. The object's apparent brightness was measured at magnitude plus 12.3 plus or minus 0.2, exceeding the stack's 3 sigma noise floor by a signal-to-noise ratio of 5.6, sufficient for a statistically valid detection. Every calibration parameter, from dark frame subtraction coefficients to sky model fitting radii, was published openly with their Python-based workflow on GitHub, allowing full independent replication. But as always, rumors moved faster than the data. Within hours of the faint Perseverance signal circulating online, social media lit up with sensational claims. Some users shared enhanced rover images showing razor-thin streaks cutting across the Martian sky, alleged proof that 3I/Atlas had been bright enough to see with the naked eye. The most viral post came from a Perseverance navcam frame dated October 3rd, showing a luminous, needle-like line arcing across the horizon. Forums exploded with annotated screenshots, red circles, and captions declaring, "The interstellar object must have caught in motion." But the numbers didn't fit. Dr. Emily Atkinson, a planetary geologist and ephemera specialist known for forensic image analysis, checked the coordinates against NASA's JPL Horizon system. The timing and trajectory matched Phobos, Mars's inner moon, to within 0.2 degrees, a near-perfect overlay. Its apparent speed, orientation, and elongation were fully consistent with a 16-second navcam exposure taken during Phobos's nightly transit. The streak, though striking, was not a messenger from another star, just a moonlit artifact of orbital geometry. The verdict spread quickly through professional channels, tamping down the viral excitement. The lesson, familiar yet newly urgent. In the search for interstellar truth, confirmation demands calibration, and patience is as vital as discovery itself. The viral streak, it turned out, was not 3I/Atlas, but something far more familiar, a Martian satellite caught in motion. As that excitement faded, another round of speculation ignited. This time, attention focused on an October 2nd Mastcam Z frame from Perseverance, showing a bright, fast-moving line that seemed to defy explanation. The streak appeared to cut across the Martian night sky at extraordinary speed, sparking claims that it might be the interstellar visitor itself captured in transit. Amateur analysts across online planetary forums measured the streak's angular velocity and compared it with 3I/Atlas's predicted motion. The results were immediate and decisive. The streak traversed the camera's field in under a second, moving at least 10 times faster than the comet's expected angular rate of 0.09 degrees per minute. Planetary geologist Dr. Emily Atkinson and others quickly verified the discrepancy. By overlaying the streak's path with coordinates from NASA's JPL Horizons ephemeris, they showed that the streak's trajectory and orientation did not match 3I/Atlas at all. Instead, it traced a completely different sky path, the kind that could be caused by a passing particle, a glint from the rover's mast, or even a cosmic ray hit on the CCD. Within hours, most serious observers had accepted the conclusion. The streak was not interstellar, but a familiar artifact of imaging physics. The event carried a clear lesson. In planetary science, every streak demands an audit. Ephemeris matching to confirm sky position, velocity checks to compare motion rates, and artifact screening to rule out dust, sensor interference, or internal reflections. The tools are public, the process transparent, and when the community mobilizes, it can debunk a viral myth as quickly as it spreads. Meanwhile, attention turned back to Mars orbit. The Mars Reconnaissance Orbiter, MRO, equipped with its HIRISE telescope, was theoretically capable of capturing the sharpest image ever taken of an interstellar object from another world, but HiRISE's narrow 1.14-degree field of view made every exposure a gamble. A single arc-second of error in targeting could send the object racing out of frame. At 3I/Atlas's speed, over 60 kilometers per second relative to Mars, even a half-second timing offset could shift its position by several kilometers. Each exposure required precise ephemeris prediction, reaction wheel alignment, and millisecond-level timing. Engineers at NASA's Jet Propulsion Laboratory, ESA's Mission Operations Center in Darmstadt, and their counterparts in the UAE and China all scrambled to coordinate observation plans. Even spacecraft not designed for deep space tracking, like the HOPE probe and Tianwen-1, were retasked to attempt long-exposure imaging through their high-resolution cameras. For the first time in human history, an entire interplanetary fleet stood ready to photograph a visitor from another star system. The alignment, the timing, the opportunity, everything seemed to converge. And yet, as the days passed after the flyby, no images, spectra, or confirmations emerged from any of the orbiters. The silence grew louder than the signal itself. Among the orbiters stationed around Mars, each brought its own unique advantage to the interstellar watch. The European Space Agency's Mars Express, equipped with its multispectral imager, and the Omega spectrometer, offered broad sensitivity across visible and infrared wavelengths. It could scan for volatile gases, map mineral compositions, and detect chemical fingerprints in the faint coma surrounding 3I/Atlas. These capabilities made it ideal for identifying unusual compounds, substances perhaps formed under alien stellar conditions far beyond our own solar system. Meanwhile, the ExoMars Trace Gas Orbiter TGO carried an even sharper set of tools. Its twin instruments NOMAD, Nodder and Occultation for Mars Discovery, and KSS, Color and Stereo Surface Imaging System, were reprogrammed for deep space tracking. Together, they were poised to capture both high-resolution spectra and multicolor imaging of the comet's passing halo. NOMAD, with its sensitivity to parts per billion of gases, could detect traces of methane, ethane, hydrogen cyanide, or even deuterium-rich water vapor, molecules that might betray an extrasolar origin. The UAE's HOPE probe and China's Tianwen-1 expanded that coverage. Though not built specifically for comet science, their wide-angle cameras and infrared spectrometers provided crucial contextual monitoring. Together, this multinational network formed the most capable set of instruments ever assembled in Mars orbit, a coordinated array spanning visible infrared and ultraviolet bands, all directed toward one fast-moving point of light. The technical promise was extraordinary. From their vantage above Mars, these orbiters had a unique geometric advantage. While telescopes near Earth were now blinded by solar glare, the spacecraft around Mars could still see 3I/Atlas from a darkened hemisphere, free from solar interference. In theory, HiRISE aboard the Mars Reconnaissance Orbiter could resolve features within the coma's structure, perhaps even detect fragments if the object were beginning to disintegrate under solar stress. Omega and NOMAD, with their ultrafine sensitivity, might capture traces of exotic isotopes, for example, unusual ratios of carbon, oxygen, or nitrogen, hinting at the comet's birthplace in another star system. Every instrument team made last-minute recalibrations. Engineers fine-tuned exposure times, optimized onboard compression algorithms, and balanced signal-to-noise ratios against the risk of detector saturation or loss of lock on the moving target. The data, if captured, could have rewritten what we know about material beyond the solar system. But then, nothing. As of October 7th, 2025, not a single high-resolution frame, spectral dataset, or raw image from any Mars orbiter has appeared in the public archives. No preliminary plots, no press releases, no confirmation. The silence was total. For an event of such magnitude, with every major space agency watching, the absence of data has become its own enigma. Did the instruments miss their target? Were the results inconclusive? Or was something seen that required review before release? No one outside mission control knows. And until the first data files surface, 3I/Atlas remains both the most closely observed and the least understood interstellar visitor in human history. Routine quick looks, press briefings, and even low-resolution thumbnail previews remain either under embargo or delayed by processing backlogs. The silence, it seems, is not the result of negligence or indifference, but of bureaucratic gravity. A mix of embargo policies, calibration bottlenecks, and, in this instance, an overlapping government shutdown that froze data processing pipelines across several institutions. For now, the world waits, aware that the most decisive data may already exist, locked behind institutional review and red tape. Somewhere inside encrypted mission servers, the truth of 3I/Atlas could be sitting quietly, waiting for clearance, calibration, or consensus. Pointing a spacecraft at a fast-moving target millions of kilometers away is an exercise in calculated risk. The ephemerides for 3I/Atlas, its predicted coordinates in the Martian sky, were updated daily, sometimes hourly, as new tracking data refined its hyperbolic trajectory. Each mission team relied on these evolving predictions to plan imaging sequences, but the process was far from automatic. Orbiters like Mars Reconnaissance Orbiter and Mars Express had to slew off their routine targets, often by several degrees, with no real-time feedback to confirm they were locked onto the correct patch of sky. Unlike Earth-based telescopes that can be adjusted in seconds, interplanetary probes operate on delay. The round-trip light time to Mars was nearly 20 minutes during the encounter, far too long for real-time correction. That meant every exposure was effectively a blind shot, a carefully calculated one-way gamble. Instrument teams programmed their sequences in open-loop mode, executing preloaded pointing commands without confirmation. Each image was, in essence, an act of faith: point, shoot, and hope the object crossed the field during the scheduled window. Adding to the complexity was the Deep Space Network, the vital communications lifeline between Mars and Earth. Every downlink session had to be negotiated and scheduled across multiple spacecraft: Perseverance, MRO, Mars Express, TGO, Hope, and Tianwen-1, each competing for limited bandwidth. Data transmission from Mars is not constant. It is a rotating dance of orbital geometry, antenna availability, and signal allocation. A single high-rise image can exceed 2 gigabits of raw data, enough to fill an entire DSN pass. Compression, prioritization, and onboard storage all play into what makes it home first, and what sits waiting for days or weeks. In that delay, speculation thrives. Scientists and the public alike refresh the archives daily, waiting for confirmation that the orbiters truly caught 3I/Atlas in motion, that their precision, luck, and timing converged for even one clear frame. But until the embargo lifts and the calibration files settle, the event remains suspended in uncertainty. Somewhere above Mars, the cameras have already looked. The detectors have already recorded, the signals have already been sent, but for now, the story of 3I/Atlas remains untold. Hidden not in the stars, but in the servers. Routine telemetry, navigation updates, and urgent command packets all compete for limited bandwidth across the Deep Space Network. Each antenna session must be shared among multiple spacecraft, and every bit transmitted comes at a cost of time and priority. Even when an imaging sequence executes flawlessly, the resulting raw data can remain stored on board for hours or even days, waiting its turn in the downlink queue. High-priority engineering packets, those confirming spacecraft health, orientation, and power levels, always go first. Science data, including the high-resolution imaging of 3I/Atlas, must wait behind the operational essentials. A missed DSN window or a brief scheduling conflict can delay transmission by an entire Martian day. In this fragile ballet of timing and geometry, even a 2-minute drift in ephemeris predictions can make the difference between capturing a once-in-history object and recording an empty starfield. There are no real-time corrections, no second chances. Mars orbiters operate on light time delay. By the time a command reaches the spacecraft, the opportunity has already passed. Teams can only plan, predict, and hope their timing was precise. Every exposure is a test of both calculation and faith. Point, shoot, and wait for the downlink. These constraints are not failures of planning or engineering. Every observation a compromise between science and survival. For 3I/Atlas, that balance was razor thin. The margin between success and failure wasn't measured in kilometers or minutes, but in fractions of arcseconds and microseconds of timing. The world waits not because of secrecy or censorship, but because the physics of interplanetary observation demand patience. Beyond Mars, solar geometry draws a hard line. As the object recedes toward the inner solar system, its position relative to the Sun pushes it closer to the glare. Soon, both Martian and Earth-based observatories will be forced into solar conjunction blackout, unable to see or communicate directly through the bright, plasma-laden line of sight. The window closes fast, and when it does, the only evidence of this encounter may rest in a handful of frames, still waiting to be decoded and confirmed. The lesson, once again, is humility. Even in an age of precision and automation, space remains a place of patience, probability, and delay. As October advances, 3I/Atlas begins its final descent towards superior conjunction, scheduled for October 21st and 22nd, when it will pass almost directly behind the Sun from Earth's point of view. By the second week of October, its solar elongation angle, the separation between the object and the Sun as seen from Earth, shrinks below the safe operational threshold of most telescopes. This blackout is not the result of policy or secrecy. It is pure orbital mechanics. When the Sun lies too close to the line of sight, scattered light and solar plasma make observations impossible. From mid-October through early December, nearly every ground-based and space-based observatory, including Hubble, JWST, and even Solar Orbiter, will be forced to stand down, blind to the comet's behavior during its most dynamic phase. Perihelion, the moment of closest approach to the Sun, falls on October 29th to 30th, right in the heart of this glare. Statistically, this is when comets are most likely to exhibit outbursts, fragmentation, or extreme brightening as volatile ices sublimate and internal stresses peak. Yet Earth will see nothing. The comet's most revealing moments will unfold unseen, hidden behind 1 billion tons of solar light. Meanwhile, the silence from Mars orbiter teams is not evidence of suppression, but of process. JPL's imaging and calibration specialists are navigating a meticulous and unforgiving workflow. Every raw frame must be audited for cosmic ray impacts, thermal noise, detector saturation, and registration drift, errors that become exponentially harder to control when tracking a faint, fast-moving target. Standard imaging pipelines, optimized for slow, static Martian terrain, begin to break down under the dynamics of 3I/Atlas, which sweeps across the sky at tens of kilometers per second. Even subpixel misalignments can smear a genuine signal into apparent noise, or worse, fabricate streaks that mimic detection. Each sequence must be reprocessed manually, frame by frame, with human oversight replacing automation. The result is not just scientific delay, it's scientific caution. A single premature release could distort global interpretation or fuel viral misinformation. The data must be clean, confirmed, and replicable before it leaves the review pipeline. And so, as Earth enters its solar blackout and Mars teams work in silence, the world waits in the quiet gap between signal and certainty. The story of 3I/Atlas continues, hidden, for now, behind the Sun's relentless glare. Even the smallest misalignment in image stacking or the failure to identify a stray artifact can create a phantom, a false fragment, a ghostly signal, or worse, erase a genuine detection. The calculus is brutal but necessary. Release an uncalibrated frame and risk fueling another viral myth. Wait for thorough review, and face accusations of delay and secrecy. Behind the scenes, engineers and analysts navigate a labyrinth of internal embargoes, calibration backlogs, and an overlapping government shutdown that has slowed non-essential data processing across multiple agencies. The result is not a conspiracy, but a bottleneck born of bureaucracy and caution. For now, the scientific world waits, not for a cover-up, but for evidence strong enough to withstand the harshest scrutiny. Only when the data have been independently verified and statistically confirmed will the next released image truly mean what it claims to show. The current working hypothesis holds that 3I/Atlas is a natural interstellar comet, not an artifact of technology or alien engineering. Preliminary spectral models suggest a body rich in carbon dioxide, CO2, but depleted or lacking dicarbon, C2, the molecule responsible for the familiar green glow of most solar system comets. If confirmed, this composition would mark 3I/Atlas as chemically distinct, perhaps born in a colder, more carbon-rich region of another stellar system. Unverified reports from early spectral reductions hint at a volatile mix and, intriguingly, slightly elevated nickel-to-iron ratios, a pattern seen in metal-rich interstellar grains, but not in typical Kuiper Belt comets. Still, without peer-reviewed publication or raw data, these remain provisional clues, not conclusions. The decisive evidence will come only from instrument-verified spectra or high signal-to-noise time series, the kind of data capable of confirming or overturning the natural comet scenario with chemical certainty. With Earth-based telescopes blinded until early December, the focus now shifts to the few observatories still capable of watching through the glare. Chief among them is Soho's LASCO C3 coronagraph, orbiting near the Sun-Earth LAL-1 point, which will continue scanning the solar perimeter through late November. LASCO's wide field and extreme solar shielding could capture 3I/Atlas as it rounds the Sun, revealing whether the object brightens, fragments, or vanishes into the solar wind. Beyond LASCO, Stereo A and Solar Orbiter's METI instrument may offer supplementary vantage points, though at lower resolution. Between these spacecraft lies the narrow corridor of opportunity, the last observational window before 3I/Atlas disappears from all view, outbound toward the outer planets and the long dark beyond. For planetary scientists and the public alike, the next confirmed detection will carry enormous weight, not another rumor or faint pixel streak, but a true, calibrated glimpse of something born beneath another sun. At its current distance and fading activity, 3I/Atlas hovers near a limiting magnitude of +8 to +9, too dim for most instruments, even from Mars' orbit. Only a sudden outburst or unanticipated surge in brightness would bring the object within visible range of smaller telescopes or wide-field imagers. Among the few assets still positioned to try, ESA's JUICE spacecraft, now outbound near Jupiter's orbit at roughly 5.5 astronomical units, may have a narrow observational window in early November. Its onboard cameras, designed for Jovian moons, could in principle attempt deep field imaging of 3I/Atlas as it moves away from the Sun. The chance of success depends entirely on geometry, scheduling, and brightness, factors that shift daily as JUICE repositions and the comet dims. So far, no official observation campaign or release schedule has been confirmed. For now, the most promising watch point lies with SOHO's LASCOC3 coronagraph, which will continue to image the region surrounding the Sun from late October through late November. If 3I/Atlas experiences a flare or fragmentation event near perihelion, LASCO's wide solar exclusion field could catch it in silhouette against the solar wind, offering the first new data since the Mars flyby. Observers are advised to monitor SOHO's C3 data stream and ESA's JUICE mission logs for potential detections in the weeks ahead. By late November or early December, as the sun's glare recedes and Earth's major telescopes regain access, the race will resume. Facilities such as the VLT, Subaru, Keck, and the upcoming Vera Rubin Observatory are expected to attempt reacquisition. Skilled amateur astronomers equipped with large aperture CCD rigs may also join the hunt, scanning predicted coordinates in hopes of confirming the returning visitor, if its brightness remains above detection limits. But the standard for confirmation is now higher than ever. Only direct instrument-backed evidence, spectral lines, high signal-to-noise imaging, or repeatable time series data will settle the debate over 3I/Atlas's true nature. Anything less risks repeating the cycle of speculation that has already clouded its story. The lesson is unmistakable. Without more off-Earth telescopes stationed beyond the reach of solar glare and atmospheric interference, the next interstellar visitor could pass entirely unseen, hidden in a geometric blind spot between worlds. As of now, the only public detection of 3I/Atlas remains the faint, carefully calibrated stacked image from Perseverance's Mastcam Z, produced not by official agencies, but by two independent analysts driven by curiosity and rigor. No high-resolution image, no spectra, no direct compositional data from Mars orbiters have yet been released. With Earth deep in solar conjunction and official datasets still under embargo, the story pauses at the edge of knowledge. Until new images or spectra emerge from SOHO, JUICE, or the resumption of Earth-based tracking in December, the strongest evidence remains that single faint signal from Mars. And so, the mystery endures. What makes 3I/Atlas unique? A question that spans worlds, suspended in silence waiting for light to return.